Hello and welcome back. This is not an Advent of Code problem video. I got a comment on my day 2 video from Daniel Sockwell, who wanted to know a little bit more about Tacks, trains, and the power operator. And I don't think that I covered that in my crash course APL crash course video, so I thought that I would make a short video here and sort of expand on those topics a little bit because these are all things that I use pretty often. Yeah, so let's start with these tack functions. So we have left tack and right tack. Now, when I was first learning APL, these basically seemed like useless functions to me. Almost like no ops. Okay, so in the monadic case, it just returns, like it just gives you back your same argument, right? And then in dyadic, it's, maybe it could be useful, but I didn't quite see how. So let's start with the monadic case. Pretty much, so we have like right tack, 1, 2, 3, we get 1, 2, 3 back. One of the most common cases where you'll see left and right tack applied is in variable assignment. So like, let's say that I have a variable that I want to assign 1, 2, 3. You'll notice that when I evaluate this expression, I don't get anything back. So like if you're building a function or something and you want to, assign the result to a variable, but you also want to return that result, you can just put a right tack in front of it, and that will, the assignment still happens, but you also get the result back. And that's, it's useful too if you're just like in the interpreter and you want to see what the results of the variable that you just assigned are. I think left tack will actually do that as well. It does. It's a little bit odd to me, but it's there if you want to do things that way. Now, in the dyadic case, this is where things get a little bit more interesting. So basically, like most APL functions, we have 2 inputs. We have a left input and a right input, and then right tack will give you the right result, and left tack will give you the left result. Again, it doesn't seem super useful, but it starts becoming powerful when you start combining it with other things. So, like if we wanted to get the rightmost element in an array, let's say that we have the numbers from 1 to 20, so iota 20, we can combine right tack with reduce, and that'll get us the last element. And so what's actually happening here, let's see, can I do something like, if I do like alpha, maybe something like this. Will this work? Yeah, okay, cool. So the way that this gets evaluated in APL with the reduce operator is, the interpreter is going to generate this expression. And remember that APL is evaluated right to left. So it's going to evaluate this first, 19 right tack 20, so it'll give you 20. And then this will be 18 right tack 20, and it'll give you 20, and so on and so forth. And I believe that this particular usage of the reduce operator is special cased in the interpreter. So it's not like actually linearly going through this thing and evaluating all these expressions. It just kind of knows that you're trying to go for the rightmost element. This will also work for arrays of arbitrary size. So if we have a 3x3 matrix of the numbers 1 through 9, we can take the rightmost column like so. And of course, we can get the leftmost column. Left tack works, the same way, right? And we can get the upper and lower columns by doing, oh geez, yeah, there we go. by using the reduce first operator. Right, so we can get the first row, and we can get the last row. Yeah, let's write tack. It's used in a couple other places, which I'll get to. Oh, it's also used, if you're writing a function, and let's say that you're performing a computation with some side effects, or what's a good example? Let's say that I have the numbers from 1 through 5, and I want to use the at operator, and I want to replace the elements 2, 3 with 10, 10. I don't know, something like this, right? You'll see people use the write tack operator here, just to separate the arguments that you're supplying to the at operator with the data that the at operator is acting on. And literally the only reason that people do this is to save some parentheses. You can just put it in parentheses and it's totally fine. But if you're like doing code golf or something, then you can save a character by doing it this way. Cool. So like you do something like this, and then let's say like you put this together and you're building a function and you're like, yeah, I don't really care about that. I want some other variable or something. Then you can use left tack. So like just imagine for a moment that this this actually, well, okay, I can help you with this imagination. So we have D is the list of numbers from 1 through 10, and let's say that for D 2, 3, we're going to again assign 10, 10, right? And so we're doing this assignment, we're performing a computation that has some sort of side effect, we're modifying the contents of D, but we actually want to return A. You will also see people using left and right tack like this. What else can I say about left and right tack? Yeah, I mean, it's, it is, these operators are pretty much as simple as you think they are. They're not doing anything crazy. But where they start to become interesting is when you use them with trains. So let's imagine that we have this file called like test.txt, and in here I'm gonna put some numbers. Cool. Yeah, whatever. And so I'm gonna do what we usually do in these videos, which is I'm gonna use ingit, and I'm gonna read test.text. Right, and there's my string. That's cool. And now let's imagine that I wanted to use this left shoe underbar to basically break apart this string using comma as a delimiter. So we have a train here that'll do it, but let's ignore that for right now. So left shoe underbar takes a Boolean array as its left argument, and the actual array that you want to partition on the right. So okay, so we can do this, but then we need, like if we wanted to partition this array, that's fine, but then we need this array on the left so that we can build a Boolean array out of it. So what you have to do is you have to assign it to some variable. So like let's say that we assign this to I, right? And now we can say, okay, left shoe underbar, and we'll do I does not equal to comma, something like this. Yeah. And so we can split the string that way. But you'll notice this is a little bit clunky, right? Because we're assigning a variable here, which we would prefer not to do if we didn't have to. You know, we have this extra expression hanging out in parentheses here. This is totally fine. It's just you can clean it up a little bit by using trains. And let me talk. Okay, so this is the rationale why you would use trains, is basically to like save you from having to assign variables like this, and just making your code a little bit cleaner by like actually focusing on the operations that you want to do. So let me talk about how trains work. A train is going to be a sequence of functions inside a pair of parentheses. Usually, it's in parentheses if it's like embedded inside of another function or a statement. Well, the simplest train is going to be just like a single function. So this is a train of one function. You know, plus in the monadic case, applied on like 3 is just going to give you 3. Plus, you know, applied with 5 and 3 is going to give you 8. Right? There's nothing crazy here. All right, let's imagine that we had like a list, and we're taking our one element train and we're doing something like this. So one element train, we're appending the left list to the right list, and we get this. When you start to build a 2-element train, what's happening is that the rightmost function will be used in the it'll be used in the dyadic sense, right? So it will take 1, 2, 3, and it will take 5, 6, 7, and it will concatenate them together. And your function on the left here will get it will get the result of the function on its right. So this is the tally function. It will return you the length of the list. And so the length of this 3-element list concatenated with this other 3-element list is 6. That makes sense. We can also do this for the monadic case. So again, let's imagine that we have our 3x3 matrix of the numbers 1 through 9. Something that you'll see pretty often is if you wanted to rotate this matrix, let's say counterclockwise. Let me think about this. Yeah, I think that's right. So we will so this is transpose and reverse, right? And the way that a 2-element train works in the monadic case is the rightmost function will apply on its argument. So we'll transpose this array, and then the result of that transposition will get fed to the left function, in this case reverse. So here we have rotated the matrix clockwise by applying these two functions. Hopefully this makes sense. So you can see that trains can be used in either monadic or dyadic cases, which is, as I've covered in my previous crash course video, are just fancy words for single argument or 2-argument functions. And the way that it works for a 2-element train is the rightmost function actually works on the input, either monadically or dyadically, and then the left function here will work on the result of this function. Everyone with me so far? Okay, let's talk about a 3-element train. So let's see, the canonical 3-element train is the average function, right? So if I wanted the average of like 3, 6, 4, 8, 1, something like this, this is how you would do it. And Okay, so what's happening here? The way that a 3-element train works is that both the leftmost, in this case, this sum operator, right? So the leftmost function and the rightmost function are each applied to the arguments of the train, and then the results of the application of those functions is fed to the middle function here, right? So if we break it down, we have the sum of the list, 22, and we have the length of the list. These are 1-element trains, right? So they just work on their arguments. And so we have 22 and 5, and that means that our train up there is equivalent to 22 divided by 5. And we get the same answer. So for a 3-element train, you take the leftmost element, or the leftmost function here, and the rightmost function, you apply both of them to the input, and then you supply the results of those functions to the middle function. Now, knowing that, let's go back to our example here, where we're trying to parse apart our comma separated list. Okay, so we're assigning a variable here. We're doing I not equal. This is fine, but if we wanted to clean things up, here's what we could do. Basically, let's imagine that we have our comma, right? This is our delimiter. And we are going to say not equal left shoe underbar and right tack. This will give us the same result. Now, what is going on here? Remember, this is the same expression as up here, right? So what's happening is the leftmost function, this not equal, and the rightmost function, this right tack, are being applied to both arguments dyadically, right? So this is equivalent to, let's see, I have this stored in I, right? So the leftmost function is equivalent to comma not equal I. And we get this Boolean vector. Okay? Now, the rightmost function is going to be comma right tack I. And what do we think this function is going to give us? Well, right tack will just select the right argument. So we get our comma separated list. Okay? And then if we take this Boolean vector and we feed it to left shoe underbar along with our string here, which we'll put it in a string, we get this. And that's what the train evaluates to. So what we're doing with this train here is, we're saving variable assignments by just having our right tack function here select the original input, right? And then we're able to feed the Boolean vector that's generated by not equals to left shoe underbar, the partition function in the dyadic case. So that's how trains work. And the neat thing about trains is that everything that I described can sort of be, it can be extended indefinitely. So trains can have as many elements as you like. The way to think about this is, let's see. Let's say that I wanted the length of the results of this application. The length is 9. Now what just happened here? So what happened is, once we start moving beyond 3-element trains, remember that APL is evaluated right to left. So what's happening is this train over here, this will be more clear if I put in more parentheses. This train over here gets evaluated first. The APL interpreter says, okay, I have at least a 3-element train here. I'm going to evaluate this. Oh, excuse me. And then, because you can think of this train as just like one function, what do we have here? We have one function on the left, and we have one big function on the right that's represented by a train. So this is a 2-element train, which means that this train on the right is going to be fed the 2 arguments, the comma and our comma separated string, and it's going to be fed to the length function. And we get 9. And you can, okay, so tally in the dyadic sense works as not match. So it will tell us if like 2 arrays are not equal. And so we can extend this to a 5-element train if we want, right? And in this case, it's telling us that, the result of this application, which is this kind of boxed array over here, does not match the original input, which is true. And if we built, another train on top of this, I don't know, let's say that you wanted to take the absolute value of this for whatever reason. This is always going to return a Boolean value, but, whatever. You can do that. And the interesting thing is that the APL interpreter is smart enough to do all of that without all these extra parentheses. So you can totally have a 6-element train like this. And what's going to happen is that you have your 3-element train first. You have another 3-element train using the results of that first application along with 2 additional functions. And then you'll have a 2-element train with the function on the left and all the applications that happened. Right? So that's trains. Now, so it's going to take a little bit messing around to get used to this. But anyway, once you get used to it, it's pretty convenient. And that's why you see people use left tack, right tack in trains all the time is just to, there's no way that we could do this parsing with just a 2-element train like this, right? Because we need this left shoe underbar to work in the dyadic case, which means that we need the original argument. So we have to supply it. And so people will use left tack, right tack in their trains in order to get the right functionality that they want out of this middle function. Like, do they want it to work in the dyadic sense? Well, then you have to supply the original argument. Anywho, there's documentation on this, as I'm sure people watching are aware. But hopefully that clears things up a little bit. I do want to dive into the power operator. So power operator in its most basic sense is just like, it's kind of like a for loop, really. So you can tell the power operator to operate like some numeric number of times. And what it's doing here, so this is going to be the starting value, this 0. And the power operator it's going to start with this 0. It's going to take this leftmost function, and it's going to successively apply that leftmost function 10 times. And our function here, if you're not familiar with this like jot function, all of this, you can basically think of this like an increment function. So each time that it's applied, it increments by 1. And we get 10 out of this, which makes sense. Maybe this will be better if I like, I don't know, let's start with like -3. We get 7 because we incremented -3 10 times. That's what the power operator means when you supply it this numeric argument. The other thing you can do is you can supply the power argument a function. And so what did I do? I think in my last video, I defined a, oh geez. Yeah, there we go. I defined a recursive function, something like this. I do w recurse w minus 1. And this will give us, yeah, this gives us the list of numbers from our arguments down to 0. You could write this in a different way. You could write this using the power operator. And the way that you would do that is we'll have a function here. So when you supply a function to the power operator, the left argument, or alpha if you're defining a like an anonymous function here, will be the result of a successive function computation. And the right argument, or omega, is going to be like the result before that computation was applied. So it'll start off being, you know, your starting value, and then it will basically be replaced by each successive function application, right? And when you supply a function to the power operator, it will continually apply the function until this, sorry, it will continually apply the leftmost function until its right function evaluates to true, right? So if we were going to write the same recursive function, you know, we could do like alpha greater than, well, because we're building a list, we'll do like neg1 take alpha 0. What is going on? There we go. Like this. So neg1 take will take the last element of alpha, right? And we can basically get rid of this guard here. And we can just, like this. Will that work? No, we need to, we'll do the same thing here. So we're doing neg1 take w minus 1 w append. I think that'll work. Yeah. So what's happening here? All right, so in our leftmost function, we are building a list. We basically, we start, our starting value is 10, right? So if we just get rid of all of this, our starting application is with 10. We get 10, 9. Because what's happening is we're taking the last element of w, which is just 10 in this case. We're subtracting 1 from it. This little operator here just means commute, so I'm just switching around the functionality of the minus sign. Then we're taking the original argument and appending this subtraction, right? Easy enough. Okay, cool. So if we apply it again, we're applying it to 10, 9. Now we get 10, 9, 8. And the power function is just doing this over and over again until this function right here evaluates to true. And this function, just to give you an idea, for example, here it's saying, okay, I have 10987. So on the right side, this is my original sort of like last input. And I applied, the function on the left, and I got this. So now I'm gonna apply my rightmost function to see if I get a true value. And you don't, because this is checking if the last element in this new application is less than or equal to 0, which is not the case. But it'll keep applying it until this condition matches. Now, you can simplify this a lot. So this is a combination that I particularly enjoy, which is the fixed point operator. What's a good example? So I think actually the power example here has, plus divide equals. For the golden mean. Yeah, that's maybe not a good example. Okay, how about this? We'll start with 0. And basically, let's say that we just generate like a random number up to 5. And let's say if 1 equals that random number, then we just return W. Otherwise, it'll be W cons 1. Well, yeah, let's like assign this value. It'll be W cons A. Okay. Yeah. Okay. So, right. So what we're doing here, we're generating a random number from 1 to 5. And we're assigning it to A. And then we say if 1 equals that random number, then we just return the original input. Otherwise, we modify the input by adding this random number to it. So what fixed point is doing is it's going to continually apply this function on the left until the results of applying it is equal to the previous result. And in this case, it'll be equal to the previous result when this random number is equal to 1. Right? Something like this. This is kind of a contrived example, but I hope that this gives you an idea of, the fixed point. And this is exactly the same as we were doing before. It's just shorthand. So you can also write like an anonymous function here where you're passing alpha, omega. That's fine too. But it's unnecessary because the function itself is, will already take care of that. So, let's see. Yeah, that's tacks, trains, and the power operator. So hopefully that's helpful. I'm going to be using this stuff a lot in my admin of code videos. Hopefully this will be helpful. I certainly don't want people to be lost when they're watching my videos. So awesome. Thanks for watching, and please do let me know if this was helpful or if you have any other concepts that you want me to cover. All right. Thank you.